just after.
I have more copies, and it's the same thing that was outside for the last few days. So.
I think I can. I don't remember what I did with my laptop.
Only the front page is relevant. I did not steal it.
No, I know. I'm not worried about it. I just don't know what I did.
So there is an announcement from the organizers.
Okay. On site we will have an excursion to Magnitogorsk. It started at 11 a.m. and finished at 3 p.m. And lunch for all participants, even for those who stay here, not coming to the excursion. We start at 3. And the bus will start from the exit. We arrive here from Chelyabinsk or from airport. It's near the restaurant and just on the right side.
Is there any way to stay longer in Magnitogorsk? If I stay longer, is there a way to return?
Okay, let's discuss.
Okay, the last speaker of the morning session is Professor Natan from University of Toronto. He will speak about the Kashiwara-Vergne problem and topology.
I have a question.
Yeah.
Do you give handouts?
The handouts I've given them all along throughout. It's just the front page of that. And I have more copies if people want. No, the handout is only the front page. Anybody wants, you're welcome to. Okay, so, right, my talk will follow a handout. The handout is on the web. The URL is over here. You cannot see it on here, but you can see it in the printed copy. And hopefully the video will be linked from there as well. Now, as for the content, so I'm giving 2 talks. The first one will be sort of on the extreme abstract end, but I will only state it without proving anything, so it will not be so daunting, okay? And tomorrow's talk will be on the other extreme end of my topic, which will be very kind of down to earth, computational formulas, etc. But the abstract end is the following. I will describe a general machine, completely general, ridiculously general. The input is anything, practically, but I'll pretend that the input is anything in topology, and then the output is a problem in algebra. Whatever you feed it in topology, the output will be a problem in algebra. And in particular, when you feed it with a particular class of knotted 2-dimensional objects in 4 dimensions, the output is the Kashiwara-Vergne problem, which I will more or less state in a minute, and then I will spend some time describing the machine itself, and then I will spend some time describing the topology, which, when fed, produces this Kashiwara-Vergne problem. Now, the Kashiwara-Vergne problem, I don't want to describe it in detail. I only want to give a sketch, roughly what it is, okay? So, what is the Kashiwara-Vergne problem? So, there is a certain statement that if you take convolutions of certain functions on the Lie algebra of a Lie group, any finite dimensional Lie group, not necessarily semi-simple or anything like that. So you take 2 functions on the Lie algebra, you take their convolution, so now you have 3 functions, and now you pull back these 3 functions to the group using the exponential map. And the statement is that under good conditions and with some normalization factors added, the convolution on the group of the 2 original functions using the Haar measure agrees with the convolution on the Lie algebra using the Lebesgue measure. So again, I'm being extremely rough. The way I said it, it's completely incorrect, but this is the general flavor. And it's enough for what I need to talk about right now. So how do you prove a thing like that? So you need to show at the end, well, you pull everything to the Lie algebra, and then you need to show that a pair of integrals on the Lie algebra are equal. One integral is just the convolution on the Lie algebra, and the other integral is the integral that corresponds to the integration on the Lie group when pulled back to the Lie algebra. So you need to show the equality of two integrals. One way to do it is to find a measure-preserving transformation on the Lie algebra that pulls back one integrand to the other. And since it's a measure-preserving transformation, it will mean that the integral of the first thing is equal to the integral of the other. One way to construct a measure-preserving transformation is to construct a vector field whose flow, for which the flow corresponding to it will be this measure-preserving transformation. And then this flow has to satisfy some conditions. It has to push one integrand to become the other, and it has to be, well, the vector field has to be somehow divergence-free, so that the flow it will generate will be measure-preserving. But now I need to construct this vector field for all the algebras in the world. And you know, if you're lucky, and in this case we are lucky, you do it by writing one single formula that works for all Lie algebras. Now, how do you write a formula that works for all Lie algebras? Well, the only thing you can use is the bracket. And since it's finite dimensional, you can also use traces of elements, okay? But, so now it's a general discussion about how to write formulas in an unspecified Lie algebras. So such a formula is really an element of the free Lie algebra, right? An element of the free Lie algebra. You know, if you have an element in the free Lie algebra in two generators x and y, so it looks like you take x and y, and you take their bracket, and then you take another copy of x and another copy of y, and you take their bracket, and then you take the bracket of these two, so it looks like a tree. And modulo some relations. Anyway, if you have an element in the free Lie algebra, you can specialize it to any specific Lie algebra. You can put x in the same, this x, to be a specific element of SL2 or some other Lie algebra, and you take y to be a specific element of the same Lie algebra, and you get an output in the Lie algebra, and basically you will have to assemble your formulas from trees. Okay? And hence the Kashiwara-Vergne conjecture, which by now is a theorem by other people, the names are listed above, is a conjecture in the following, which reads more or less as follows. So there exists two infinite series f and g in the completed free Lie algebra in generators x and y, such that these two series satisfy two relations. The first relation amounts to saying that the first convolution gets pulled to the other. When you translate it to, you know, the vector fields that these two series represent, it amounts to saying that one convolution gets pulled to the other. And then there is a second relation, which is written in the world of cyclic words, and cyclic words are really traces, and they make sense in the free Lie algebra as well, because there is a map from free Lie algebras to cyclic words by sort of closing a tree, and then what you're left with is a cyclic word.
It seems that you have 0 in your product. 0.
Where? Here? Possibly. Oh yeah, that was a 0, you're right, because I took the commutator of two equal things. Okay, let's modify it. Let's add another x here. Okay? But anyway, the second equation is written in terms of cyclic words, and it amounts to saying, after translation, it becomes the statement that the vector field that I mentioned before is divergence free. So it produces the flow corresponding to it will be a measure preserving transformation. Okay. The only thing I really want you to remember from this is that it's a problem, you know, clearly structural about Lie groups and Lie algebras, something about the relationship between convolutions on one and convolutions on the other. And in order to solve this problem, you need to solve equations in a graded space, in fact, completed graded space. I should have said earlier that the Freely algebra is graded by essentially the complexity of the tree that appears here. And that's all. I'm going to describe a machine that produces such problems. Problems about solving equations in graded spaces. Yes?
You didn't say anything about uniqueness.
No, I didn't want to say anything unique about uniqueness. There's no uniqueness. F and G are not unique.
Yeah.
Okay. I hardly said anything about actual content. I'm just describing the shape. Okay, the shape is there is a problem in Lie algebras, and and it becomes a problem about specifically algebras, but all specific finite dimensional Lie algebras, and it becomes a problem about solving equations in the Freely algebra. Yes?
If the solution is not unique, it makes more sense to describe the space of solutions.
And I will. And I will. Okay. Yes?
So your Lie algebra is infinite dimensional, right? This free Lie algebra.
Yeah.
How do you make sense of the trace in this way?
So the Freely algebra, it has nothing to do, it is not the algebra in which convolutions are taken and on which vector fields live. It's actually different. The Freely algebra is essentially the space of all formulas you can write which make sense in every specific Lie algebra. Okay? And the cyclic words, well, so the Freely algebra is the space of all formulas that take as input elements of the Lie algebras and output elements of the Lie algebra. The cyclic words is the space of all formulas that take as input elements of the Lie algebra and as output produce a scalar. Okay? So these spaces, FL for Freely algebra and cyclic words are not, they're sort of the universal replacement of, they're spaces of formulas. They're not the Lie algebra itself. I am not taking a trace in the Freely algebra. I'm only saying take the vector field which is represented by some pair of elements in the Freely algebra, its trace is represented by some element in cyclic words. Okay? Anyway, the details don't really matter. Only the shape, the overall shape. Now the details will start matter. Will start to matter. Because now I want to describe the general machine. And I'll pretend that it's less general than it is and start with a group. Any group whatsoever. So that's very general already. Okay? So start with a group G. So let G be a group. And let K be the group ring of G over the rationals, let's say. It's not very important. So basically, it's the set of all linear combinations of elements of G with coefficients AI, which are scalars in Q. Now, let I be the augmentation ideal of K, of the group ring. So it's the set of linear combinations for which the sum of coefficients is equal to 0. The moment you have that, and well, the moment you have a group, you have the group ring, you have the ideal, and then you can look at powers of the ideal, and the second power of the ideal is contained in the first power of the ideal, the third power is contained in the second, so you have a descending filtration. And you can look at the associated graded space. So let's call A the completed associated graded space of K, and it's just the direct sum as m goes from 0 to infinity of augmentation ideal to the power m modulo augmentation ideal to the power m plus 1. Now, you can ask, who cares? And one example, one reason why people in topology should care is because it's closely related to Vasiliev or finite type invariance. So, if, for example, K is the braid group, or let's say the pure braid group, G, sorry. So K is the group ring of the pure braid group. And bear in mind that the augmentation ideal is generated by differences of elements. So the augmentation ideal to the power m plus 1 is generated by products of m differences. So things of the form x1 minus y1 times x2 minus y2 times and so on up to m plus 1. And then, well, what is k dual? So k dual is linear functionals on the group ring, so these are just functions on the group, so these are invariants of elements of the group, so these are braid invariants. And what is k modulo im plus 1 dual? So these are invariants that vanish on I to the m plus 1, so they vanish on m plus 1 times iterated differences. So these are precisely what is called finite type invariants, you know, in knot theory. So we care about this space. Now, if you start studying this space, so the set of all such duals, you find that in order to understand this, almost the first thing you need to do is to understand that. So, so this space A is highly relevant in topology. Note also that A itself inherits a product from the group, so it's an algebra. And now I come to the crucial definition. So an expansion for the group G is a linear map from K to A that has the property that if you evaluate it on an element gamma of I to the m, then the result has the following shape. Now, in principle, if you evaluate it on an element of I to the m, the output is in A, and A is the space of infinite sequences of elements in I to the m modulo I to the m plus 1. And the condition is that when you evaluate Z on an element of I to the m, you get 0 in the first m minus 1 spots, in fact m spots because we start counting at 0. And at spot number m, you get gamma itself, except modulo im plus 1, so the image of gamma modulo im plus 1. And beyond that, I don't care what you get. It doesn't matter. What? Sorry?
There is a rational vector space, linear.
Yeah, everything here is over Q.
So it's just a rational vector space.
Yeah, yeah. Though there are versions of this definition when you change the field or the ground ring, it doesn't really matter. Now, if in addition your expansion Z preserves the product, so it maps the product in K to the product in A, I will call it a homomorphic expansion. Okay? And I should say that in the world of finite type invariants, this is what corresponds to a universal finite type invariant. So in the case of ordinary knots, that would be the Kontievich integral.
But why do you need need to be a field, not just a fact.
The definition makes sense over any ground ring, but later, but the theorem is over Q. Okay? Maybe the simplest example, so let K, so it's actually not quite in the same pattern, but it's very, very close, and it justifies the name expansion. So let K be C infinity of Rn, and instead of the augmentation ideal, take the ideal of all functions that vanish at 0. Now, I to the m in this case is the set of functions that are products of m functions that vanish at 0. So these are functions that vanish like x to the m. And then Im modulo I to the m plus 1 is exactly degree m homogeneous polynomials. Okay? And so A, the direct sum of all of these Im modulo I to the m plus 1 is the set of all power series. And then an expansion, according to my formal definition, will be a map from K, so from C infinity functions, to power series, which satisfies a certain mild condition. And a homomorphic expansion will also have to map the product of two functions to, well, their expansions will have to be the product of the expansions. And then the Taylor expansion is an example of such an expansion. In fact, it's not unique. There is more than one expansion in this situation, but if you add another mild condition about the behavior with respect to a certain coproduct, it becomes unique. So somehow the point is that the notion of Taylor expansion makes sense in ridiculous generality. It makes sense for every group, and in fact, as you will see later, it makes sense in even much higher generality. Okay? And the point of my talk is to show that when you look for expansions in a certain place in topology, you end up asking yourself problems about convolutions, about in Lie groups and Lie algebras. Now, unfortunately, this is a 45-minute talk, so I cannot go through the details of that, but this is another fun interpretation of expansion, so I'll just say very, very quickly. Roughly speaking, if you have a filtered space and you mod out by successive elements in the filtrations, then, and since this is a descending filtration, then at every stage you end up seeing the space in a higher and higher resolution. So in some contexts it would become, you start from a picture of buildings next to a lake. Maybe I should magnify it so that you'll see what I'm talking about. And then you look at this picture at sort of less and less pixelization. And in fact, if you remember sort of slow internet connections, pictures used to be transferred in this way. Sort of you'd first see sort of a vague picture and then it will become sharper and sharper as you wait for more data to come in. If you think a little bit about what this space A is, it becomes the space of, so the degree n piece of A is exactly the additional information you need to transmit about the picture if you have already transmitted part n and you only need to know part n plus 1. So an expansion is essentially a method of transmitting pictures so that on your web browser it will appear like this sequence. Okay? And a homomorphic expansion is if you try to do it in a way that is compatible with various operations on pictures. It's highly non-trivial. Okay, it's a serious problem. Anyway, back to mathematics. So, in the finitely presented case, so if the group is finitely presented, namely it's generated by finitely many generators, and these are subject to finitely many relations, finding an expansion Z is just a matter of finding the value of the expansion on the generators, and these values have to solve the relations. So finding an expansion amounts to solving a system of equations in a certain graded space. And this is true in complete generality. Now I'm done describing the machine, and now I want to start talking about the domain space of this machine. Is it okay if I move to the next slide?
Can you explain the meaning of the letter omega?
Omega, where? Here.
Everywhere.
Here. Oh, it's defined at the very top of the page to be a certain URL.
I see.
Okay?
Yes.
So, you know, if you want the reference for the proof of the theorem, you go to that URL, add slash and WKO. Okay? Okay, anyway, so the domain, in my case, my algebraic structure, what replaces the group is a certain algebraic structure made out of four-dimensional knots, or two-dimensional knots in four-dimensional space. So I want to tell you a little bit about them. And in fact, you know, I know all of you are topologists, but it's still fun to spend some time visualizing them. So here is a beautiful picture of a four-dimensional knot drawn by Carter and Saito in their book on the subject. And here are two more drawn by Esther Dalvik. So let me tell you how to read these pictures. So you take your four-dimensional knot and you project it to 3D. And then it becomes just a two-dimensional surface in 3D, but it has self-intersections. So what we do in this case, what? Yeah, 2D knot in 4 dimensions. Right. So the 2D knot becomes a surface, and it has self-intersections. And then what we do is we do the same thing as what we do in ordinary knot theory. Namely, whenever something goes above something else in the coordinate we don't see, we, the lower thing, we put a cut in it, sort of to indicate that it's below. Okay? So we draw the surface of the knot in 3D, but we make cuts in it wherever it is hidden by something whose t-coordinate is higher. So let's try to read this lovely knot. So let's start maybe here and go to the left. If I go to the left, I see a tube. It's a tube, 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 tube. This tube goes over something, because it goes in the fourth coordinate, because the other thing has a cut. Then it goes up, opens up to a big drum. Part of the drum goes below where we've been before, but then another pipe comes out of this drum, goes over something else, and then below something else, and then closes up. And when it closes up, it goes over something. But overall, what we have seen is just a tube which gets capped. The parameter space is just a tube which gets capped while going over and under various things. Now let's go to the right. So I have my tube, I go to here, I go under some place where I've been before, then my tube thickens, becomes a big drum, and as it thickens and becomes a big drum, it goes over something else, and then the drum gets capped, and as it gets capped, it goes under something else. So topologically, from the perspective of the parameter space, all I did was I added to the tube another cap on the other end. So overall, this creature is just a sphere. But in R4, it is knotted. So this is my first example, and here's the second example. So the idea here is to use the rainbow flag to indicate the fourth coordinate. So basically, things that are high in the rainbow flag have high t-coordinate, and things that are low have low t-coordinate. So here is a certain two-dimensional knot in R4. It is projected to R3, so we see only a surface. Actually, it's a bit hard to see what's going on here. So here is this surface cut in half, but the other, you know, if you want to make it, to generate the thing back again, you just make two copies of this and clump them together, put them together. And then you can read the fourth coordinate from the color. So again, this is just, well, okay, if you start from here, it's a capped tube. If you go in the other direction, again, it's a capped tube. So this is again a sphere. And in 3D, it appears to have self-intersections here, 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 and here. But in 4D, these are different colors, so there is no real intersection. Now, it's not obvious that it's non-trivial, that this is a non-trivial knot, but it is. If you at least naively try to undo it, so one way you could try to undo it would be to pull this cap out. But you can't, because at some point along this sort of thin tube here, the color is the same color as the color of the cap. So if you try to pull it, you'll get a clash. Okay? If the inner tube here, the thin part of the tube here, was red all the way from here to here, then you could pull it out and then it would be the unknot. Okay? So these are two examples, and now I want to switch and talk about the generators. So sort of the basic knotting phenomena that can happen in 4D. And there are several ways to describe them, and the lovely thing is that one of the ways is very close to ordinary knot theory. So from this point on, an ordinary crossing of two purple lines drawn in the plane will actually represent something in 4D. And let me show you three different ways of understanding what this 4D thing is. So one way is the way shown here. So it's this sort of double inflation procedure. You first of all inflate the purple lines into bands still in 3D, as shown here, and the bands actually intersect each other. So there is this dashed line here of intersections between these two bands. And then you do the second inflation, and the second inflation is to take each of these bands, and well, what you do is you make two copies of each one. So you make two copies and you put them one on top of each other, and then in the fourth coordinate, you pull one copy out, up, and one copy down. But you do this amount of pulling, the amount by which you pull is proportional to the distance from the boundary. So the boundary doesn't get pulled out at all, but the middle gets pulled out a lot, and the other boundary again doesn't get pulled out at all. And for the band, so and again I make two copies, so one gets pulled up and one gets pulled down. So overall, this band becomes a tube in 4D. And this one is another tube in 4D. And these two tubes interact in a certain way, but they no longer intersect, because this band is wider than this one, so it's hard to see in the picture. So the middle of it gets pulled more than this one. So in 4D, there is actually the intersection disappears. Okay? You know, I wish I had time to show you. There is a little video clip sort of showing it moving around a bit. I think I'll skip it, but if I click here on the computer, it will show it. Yes?
Is there a crossing in the Carter-Saito knot?
Sorry?
In the Carter-Saito knot? Can you show that that was crossing?
No. But I can show, I mean, this pair, I mean, wait a minute, okay? Just in a minute the example will be on the board, okay? And so here is a view using cut surfaces. So one tube is shown here, the other tube is shown here, and it's cut in a certain asymmetric way to show its four-dimensional view. And well, the last view is us moving or flying rings. So the idea is that, well, I mean, this is a part of a knot, so it's still just a braid. And, you know, ordinary braids are points moving around in a plane. If you go one dimension up, you have to think about rings. Here is one ring, here is another ring. You have to think about rings flying around in R4, in R3, sorry, in R3. And then if you have two rings, one can pass through the other, comes on the other side, come out on the other side, and this is in fact what that is. So the ordinary crossing becomes sort of two rings flying through each other. Okay. Then there is a second ingredient that may appear in four-dimensional knot theory, and this is the so-called virtual crossing, or the V crossing. So again, it looks like a crossing, except I don't bother to indicate which one is under and which one is over. And the double inflation realization, well, the first inflation is you just take two bands and you put one on top of the other as shown, and it doesn't matter which one is on top and which one is below, and then you inflate. In 3D, these two pictures are different. In 4D, these two pictures become two tubes that are, well, one is above the other, or one is above the other way, but in 4D there is no distinction between these two ways for two tubes to pass each other. So, so both of these are in fact the same thing. If I were to show you a lovely movie, I'd click here, but I won't do it. And finally, as a flying ring movie, it's the movie in which the two rings trade places, not internally, but externally. And then it's clear that it doesn't, since the rings are flying in 3D, it's clear that it doesn't matter whether they trade places this way or that way or above. All ways of trading places externally are the same. Now, there are a few more ingredients you can put in a 4D knot. So you could put a cap, and my notation for this will be a line that ends. The first inflation will be a band that ends, and when you inflate it once more, you just get a tube that gets capped. And then the last ingredient that I need is the plus vertex. I also need the minus vertex, and it's the same with some orientation changed. But the plus vertex is actually a singular thing. So if you wish, it's a foam embedded in 4D. So the best way to view it is to view it as a movie of flying rings again. So you get a pair of rings, they fly until they coincide, and from that point on they become one and fly together. Okay? So, you know, this is just an ordinary vertex brought one dimension up. So it's like having a vertex in ordinary knot theory. You have 2 points moving around, then they coincide and start moving together. So 1 dimension up, it becomes the picture shown over there. And then a few examples, and I'm running out of time, so I will do it very quickly. So here is a long knot. So I have a purple line starting at -infinity, ending at +infinity, and it has both ordinary crossings and virtual crossings. When you inflate it, the first inflation becomes, well, a certain band that starts at -infinity, ends at -infinity, and has either singularities like here and here, or passes, non-singular passes as here, and again, it doesn't matter which one is up and which one is down here. And then when you inflate it a second time, you get a tube in R4, starting at minus infinity, ending at plus infinity, and doing something crazy in between, and I cannot show it. I mean, I cannot draw it. That's one example. Second example, apply the double inflation to this. And now you have, well, a cap connected by a tube to another cap. So overall it's a sphere. And when you actually perform the inflation, you get this picture. Well, here it's, well, this is the picture with color, slightly different color coding of heights. But it's a two knot in R4. And this is exactly the Dalvik knot that I've shown before. Okay? With just different colors. So this also answers Matt's, wait, it was Matt who asked this, right? Yes? So this also answers your question. If you want to see crossings in the knots I've done before, well, the Dalvik knot is actually a two-crossing knot in that sense. Okay? Good. So now let me describe the set of topological things that I will study, the space of topological things that I will study. So it's the space WK, and WK is the planar algebra, that's what PA stands for, generated by the four generators that I discussed before. So the crossing, the virtual crossing, the cap, and the, well, actually the plus and minus vertex. Now, what's a planar algebra? I could give a formal definition, but not in 5 minutes. But you don't really need a formal definition. Roughly what it is you have objects, and the objects are little pictures drawn in the plane, like these squares here. And then you can compose them by putting them side by side to make bigger objects drawn in the plane. And, well, here is a composition of 4 objects to get one bigger object. And the word planar here stands for the fact that you don't just compose like in a group linearly one after the other, but the composition can go both from left to right, but also up and down, and in fact in other planar directions as well. Okay? So effectively, it means, so again, without the formal definition, but effectively, if you look at the planar algebra generated by these pictures, you get all pictures of this kind you could possibly write. Okay? Except that's not quite what WK is. WK is the planar algebra I just described, modulo a bunch of relations. And these relations are relations that are satisfied by the 4-dimensional images that these pictures, the 4-dimensional things that these pictures represent. So it's a lovely exercise to check that, the Reidemeister 2 rule holds for flying rings. So it becomes basically, well, you have one ring flying in through another one, and then it flies out the same way, and topologically it's clearly trivial. Then there is a Reidemeister 3 relation for flying rings. Then there is a virtual Reidemeister 2 relation. So the virtual Reidemeister 2 relation becomes the fact that if 2 rings fly externally across each other and then they fly back externally, it's as if they just stayed in place. It's lovely to interpret all of these relations, but I don't have time. But let me just indicate that there is some asymmetry in this. So in ordinary knot theory, sort of being the understrand and being the overstrand is almost the same. But here the understrand and the overstrand have different meaning. The under means the ring that flies through, and the over means the ring which is bigger. and they behave differently in certain circumstances. So there is a relation which says that you can slide over strands across virtual crossings, but you cannot slide under strands over virtual crossings. So there is some asymmetry, and if I had a few more minutes, I would explain this symmetry by a bunch of few pictures, but I don't think I have this time. Now, the algebraic structure that I want to consider is actually a bit richer. So I have these generators, and I make a planar algebra out of them, but I can also do two types of so-called unzip operations. So basically, well, you know, this corresponds to unzips in ordinary knot theory. So in ordinary knot theory, there is an unzip operation which goes from a picture like this to a picture like this. So if you have a knotted graph, and you have an edge connecting two vertices, and of course the edge could be knotted, right? You could replace this edge by a pair of parallel edges. You need a framing, okay? And that's the unzip operation. There is a similar unzip operation in our case. So if I have two vertices, I can unzip and get well, something that looks like this. But what it really means is that if you have two rings, they fly together, they coalesce, they fly into each other, they become one, they fly together for a while, and then they split again. You can unzip and turn it into two separate rings that do the same dance as before, but epsilon away from each other. Okay? So that's the annulus unzip, because the unzipping here appears happens along an annulus, the boundary of this tube. Okay? And there is similarly an unzip along a disk. So if you have two rings that fly, coalesce, and then fly together for a while and then get capped, you can replace it by, well, two rings that fly become near each other, fly near each other, and then each one individually get capped. So these are two further operations that I have on my knotted objects. And I'm now 1 minute over time, so I'll just say that the machine I described before, the machine starts from group theory, but it doesn't have to start with group theory. All I needed was to have a multiplication operation. If I have many multiplication operations, as I do now in a planar algebra, the more the better. Okay? So the machine generalizes to arbitrary algebraic structures. So if you take the machine I defined before, use it on the algebraic structure I have just described, then it automatically produces a graded space. The graded space turns out to be the space of something related to Freely algebras and cyclic boards. Inside this graded space, if you wanted to construct a homomorphic expansion, you have to assign values to these things. These values will be the unknowns F and G of the Kashiwara-Vergne conjecture, and these unknowns will have to satisfy a bunch of relations which reduce to the equations that I wrote before. And overall, we get the following theorem, that there is a bijection between the set of homomorphic expansions for WK. This is totally well defined by now. Okay, I mean, you might not completely see what it means, but WK was defined and the notion of homomorphic expansions was also fully defined. So we have a bijection between these homomorphic expansions and solutions of the Kashiwara-Vergne problem. And I should just add that this is the tip of a major iceberg. There are lots of other interesting problems in graded algebra that correspond in a similar way to studying invariants of various topological things. and I'll end with propaganda, and sorry for going 3 minutes over time.
So Kashiwara-Vergne has maybe something to do with the algebras or associators. And here you're talking about two nodes. Is it because of your own history with Bannoe homology that you went to four space? Or?
No, no, unrelated. This is completely disjoint from Bannoe homology. Also in my personal historical sense.
So why are those things become two knots?
Oh, what?
I mean, why are those solutions having to do with knots at all?
That's a good question, but you can ask it much earlier. Why is it that Lie algebras have anything to do with knots? It's well, no, but even with ordinary knots. So maybe the reason why Lie algebras appear within this class of two knots is because, well, the description is very much not theoretic, except you add these virtual crossings. So somehow Lie algebras arise in the same way, or in a similar way. But why did they arise in knot theory to start with? That's an unexplained miracle in itself. Yes.
The easiest examples of two-dimensional knots in four space to visualize are the so-called spun knots of Zeeman.
Yes.
You take a knot like that and then you spin it.
Yes.
How would these look in your formulas?
These would be the classical knots. So if within ordinary knot theory embeds into WK by just forgetting all the fancy nonsense. Okay? And ordinary knot, the image of ordinary knot theory is exactly the span knots.
All the spun knots and only that.
I think so. Though
Are you sure?
am I sure? Okay, I lied to you. I lied in a certain place. So you see, reality is a bit more complicated. Sorry. So WK maps into 4D knots, and these are all the relations that we know. We don't know if there are more relations or not. So assuming a reasonable conjecture that these are all the relations, then I think this is exactly span knots, yes.
Just one more question. So in your theorem with Zuzi, if there's a bijection, does it also imply that the set of solutions is non-empty?
No.
Oh.
As it stands right now, it may well be that both sets are empty.
Okay.
But both are non-empty. That requires a separate.
Okay.
Now I
It's a
mentioned
separate
that.
theorem.
Now I mentioned that this is a tip of a major iceberg. Now another piece of the iceberg is, in fact, Alexei somehow hinted at it. There is a map from U theory, from ordinary knot theory, into W knot theory, and you can sort of put the map into the machine as well, and it becomes the fact that from associators you can construct solutions of Kashiwara-Vergne. But these are other parts of the iceberg. I'm not talking about them right now.
Last question.
So how do you define the filtration or the analysis of the augmentation idea?
Exactly the same way. So instead of looking at so you take this planar algebra, you allow linear combinations with coefficients in Q, except that you preserve the skeleton. So you have to look at linear combinations that have the same kind of underlying combinatorics, in which all elements have the same underlying combinatorics. Then you look at linear combinations in which the sum of coefficients is equal to 0. That's the augmentation ideal. And then you look at powers of the augmentation ideal. What does it mean, powers of the augmentation ideal? It means powers using all available operations. So instead of just the group multiplication, you use all multiplications.
I think it's a good moment to thank the speaker again. There's a lunch break until 3 p.m.
Oh, it's a kid's toy. I took a picture of domino. Yeah, I took a picture of pieces from some kids'
If you want to go ahead. So to do your guy, like A1.
No, it doesn't follow. These are extra operations. So the algebraic structure that I study, I can apply my machine in any algebraic structure.